All right, we're ready to try to tackle Newton's second law of rotations. Um, that involves some new quantities. And when we talk about just Newton's second law for linear translations, along X, Y, Z, you have some of the forces is equal to the inertia of the object the forces are applied to, and the acceleration the object is going to experience. For rotations, it is a little bit more complicated because not only do we have to keep track of forces, but where those forces are applied um, relative to a rotation axis. Um, that means that instead of the sum of the forces, we're going to do something called the sum of the torques to get the net torque acting on an object about a rotation axis. And that is equal to the rotational inertia, which is how the mass is distributed relative to the rotation axis times an angular acceleration, alpha. In terms of dimensions, we're going to have Newton meters on one side, and then on the other side, we have kilogram meter squared for rotational inertia and radians per second squared for angular acceleration. You can drop the radian, and so it's be Newton meters on both sides. I'm going to talk a little bit about how to calculate a torque for a fixed axis of rotation. We'll do that first as sort of an easiest place to start. But don't be too mystified about where this equation is coming from. Basically, you're taking Newton's second law of motion, uh, and you're going to pick a rotation axis and take r cross both sides of the Newton's second law of motion to get Newton's second law for rotations. So it's an additional set of information for predicting the motion of a body, but it doesn't come from like thin air or from nowhere. You're essentially like taking a moment of Newton's second law of motion by taking both sides of the equation and doing the operation of R cross product, the sum of the forces, and then R cross product how the mass is distributed. So this is has a basis. All right. So if I have a fixed axis of rotation, I want to drop down a line that goes through the axis of rotation and includes the point where the force of interest is applied. So you're wanting to get the torque caused by this force. So we're going to define one direction is the direction from the rotation axis to the point where the force is applied. And that is going to be quantified with a position vector r. And then we have the applied force. And that applied force is going to define what's called the line of action, which is the second dashed line. And those two lines are going to make an angle, label phi. Computationally, the torque caused by the force F is the magnitude of this position vector. So I have R, the magnitude of the force F, and that is the sine of the angle phi. And this angle phi is also this angle phi. We'll turn everything into a vector in a bit. We're just working with a fixed rotation axis at first. And so we just have a convention then for sines, SIGNS. If I look down on the situation and the applied force is trying to cause a rotation that is counterclockwise, then that is a positive torque. So in this drawing, it is. If the force were trying to cause a clockwise rotation, then it would be a negative torque about this axis. And that goes back to our convention in physics that a uh, positive rotation is a rotation that is counterclockwise when viewed from above. We can think about what sine phi is doing in a couple different ways. The first of which is we look at the line of action and you want to pick the shortest distance from the line of action to the rotation axis. And that is called alternately a moment arm or the lever arm, depending upon what textbook you're reading. I was saying it's most commonly known as the lever arm. And so the shortest distance from the line of action to the rotation axis is going to be that perpendicular distance. So this is a right angle. And that gives us an interpretation of what sine phi is doing. What it's doing is taking the position vector r and getting this shortest distance component, r perpendicular. And it is effectively that distance that goes into the torque equation if I'm keeping all of the force. The interpretation of the lever arm is I'm going to get the most effective torque out of a force possible if the force is perpendicular to the position vector. If it's not, then it's not all of the position vector that matters. It's just going to be a fraction of it. And how much? It's going to be this perpendicular component. I would get the same torque if at R I acted with the force F, or if I acted at the location of R perpendicular with a force F. So it's been foreshortened by this fraction sine phi. All right, so that's one interpretation of what sine phi is doing. Another way you can interpret it is that think of breaking the applied force into a radial component and a tangential component. The radial component can't cause a torque because it's not going around the axis in any sense. It's either radially away from the axis or radially towards the axis. And if you push on a door into the hinge, you're well aware it's not going to rotate. So all that can matter for a torque is how much of the force is along the tangential direction. So in calculating a torque, we can think of it is all of the position vector times just the tangential component of the force. And you can use any of those three ways. Torque is equal to RF sine phi, all of the magnitude of R, all the magnitude of F. Or you can try to be clever. It's not all of R, it's just the perpendicular component. Or it's not all of the force, it's the tangential component. Any of those is going to give you the same answer, and one might have a better physics interpretation to make something clearer in your mind for why it happens the way it happens. So just be open-minded to all three. All right, so let's try a little example that hopefully we can do in our head. You have a pretty whopping big piece of wood here. It is 4 meters along the long direction and 2 meters along the shorter direction. And there are two equally strong forces applied at those positions. This force is straight down at 22 newtons. This force is straight right, also 22 newtons. And we want to get the net torque, its magnitude and direction. And the rotation axis is at the upper left-hand corner. So two torques, let's try to add them together correctly. So work through it, talk it over with your neighbor, and then unpause the video and we'll talk about it together. All right, so let's see how we arrive at minus 44 Newton meters. So the force here is 22 newtons and it is acting with a lever arm of 4 meters. So we're at 88 Newton meters, and it is trying to make the block of wood rotate clockwise. So we have a negative torque. minus 88 Newton meters. This force has a lever arm of 2 meters and is trying to make the block rotate counterclockwise. So boom, boom. I'm having a torque coming out of the board at me. We'll get to that in a little bit. So that is 2 times 22 is 44. This is plus 44 Newton meters. I add those two up together and I have minus 44 Newton meters. And so that is 44 Newton meters clockwise. All right, a little bit more conceptual. When you use pruning shears to cut a branch, we know it is better to insert the branch closer to the hinge than near the tip of the shears. Which one of the following statements best explains the reason this observation is true? So it's like cutting something with the scissors or shears or pruning shears or whatever, even holding it with the pliers, right? We know we can get a stronger grip or a better cut if we are closer to this pivot point. And what explains why that is the case? So read through your 5 options, talk it over with your physics partner, and then we'll go over the answers together. All right. So you think of this as being the same torque anywhere along the cutting edge of the shears, but for a smaller distance from the pivot point, that's going to be a larger force. So it's going to be more effective at cutting. So torque acting in the branch is smallest near the hinge is incorrect. Torque is the same anywhere along the cutting edge. So it's not largest near the hinge. The torque exerted on the shears yields the greatest force on the branch nearest the hinge. So it's the product of R times F is constant. R is small, F is big. The long handles determine the force exerted on the branch. That's not true. That tells you what the torque is. Same torque is exerted on the shears of the branch, regardless of the force applied to the handles. The same torque is exerted on the shears and the branch, regardless of the force applied to the handles. No, you're causing a rotation of the handles, which is going to be reflected in a torque causing a rotation of the shear. So that is not true. All right. There are lots of elements of gymnastics, feats of dexterity. If you think of like circus performers, that these all have their roots in understanding torque. So as an example of that, go to a circus and a clown is balancing a step ladder on their forehead. And if you pay attention to what the clown is doing, you're going to see that the clown is looking up and is bobbing their head a little bit, right? You notice that the clown is continually moving to keep the ladder from falling off his forehead. Why is that movement necessary? All right. So read through the different possibilities, think about what you think the answer is, and then let's talk about it together. The clown is doing this to keep the center of mass of the ladder directly above his head so that the normal force in the forehead can cancel out the weight and there is no net torque. So if you keep the center of mass directly above his head, then there is no torque because there is no perpendicular component of the force, no rotation. So you can keep the ladder in equilibrium. Right. Let's look at that one. The clown is trying to apply a torque to the ladder in the direction opposite to the other torques on the ladder. Nope. No, there's really nothing you can do to apply a torque. All you can do is keep the center of mass of the ladder supported. By rocking the ladder on his forehead, the ladder will be more stable than if it were stationary. This is similar to riding a bike. No, it is not similar to riding a bike. This is not about angular momentum in the wheels. Movement is not necessary. No, very much is necessary, or else you're going to have a ladder on the ground very quickly. You get little perturbations of the ladder going one side to the other. As soon as the center of mass would pass outside the base of support, it would start to experience a torque and tilt over. So it is very necessary. All right, little puzzle. A long board is free to rotate about the pivot. So that's the triangle. So each of the 4 configurations, weights are hung from the board as indicated. In which of the configurations, if any, is the net torque about the pivot axis the largest? Neglect the weight of the board. So we're neglecting the weight of the board. And we want to find the case where the net torque about the pivot point is largest. So need to do a net torque and keep track of the signs of the individual torques going into the sum correctly. And then go through and try that out. And we'll talk about it together. All right. So I had a little quick jot calculation here. If I look at the first situation, I'm 1, 2, 3 units of length, whatever that happens to be, to the right of the pivot point. And there's this M, it's actually mg to make it a weight, but it's the same G for everything. So I'm just going to write it out as 3M is the magnitude of the torque caused by that weight. And it is trying to make the board rotate clockwise. So that is minus 3M. For case 2, I've got 1, 2, 3, minus 4M plus 1M is also minus 3M. In case 3, I've got 1, 2, 3, minus 3M plus 1M is minus 2M. So far that's tallest of allest. And then in the last case, I've got minus 2M, a minus 3M. So far on the right-hand side, I have a minus 5M. On the left-hand side, I've got a plus 1M. So minus 5M plus 1M is minus 4M. So the largest torque weights around the board is indicated is the net torque about the pivot axis the largest. So those are the net torques. Which one of those is biggest? Minus 2M. So it is case 3. All right. Last one, we have a box, and the center of mass of that box is indicated by the dot. We put the box on an inclined plane in different orientations. In which of the 4 orientations shown, if any, does the box tip over? So think about what's going to happen in each of those cases, and then let's talk about it together. All right, the only one where it's unstable and will tip over is going to be in case C. A way we can see this, take direction straight down. And that's going to be the direction that the force of gravity acts at the center mass of the box. That is going to make a torque, say about this point. Okay. That is trying to rotate the box into the inclined plane. So the normal force can stop that. Right. So this one won't rotate. Similarly, if that's a force of gravity, I'm going to make a rotation axis at that point. Again, that torque is trying to make the box rotate into the inclined plane. So just to be clear, so there's my position vector, and there's my force vector. There's R, there's F. And the normal force from the inclined plane could cause a torque to cancel that one. So that's stable. We do D, there's my force, my rotation axis again, circle the dot, position vector. This is trying to make a torque, rotates it into the inclined plane, and the inclined plane's normal force can counteract that. Yay. All right, what happens with C? So there's force of gravity, going straight down. There's my rotation axis that I picked. There's, oops, that's not a great line. It's just that. All right. Draw in a position vector. All right, so now R cross F is going to be a counterclockwise torque. And there is no normal force that can prevent that from happening. So once I have this force acting outside of the basis support, this is going to topple over. And you probably are aware of this from everyday life of being a bipedal creature in a gravitational field. If you lean far enough over, front, back, side to side, that your center of mass is outside of the base of support from your feet, you're going to start to rotate and start to topple over. That's what's actually happening. You're in a situation where the normal force from the ground on your feet can't exert a torque that can keep you stable any longer, because the normal force is just going to be a repulsive force. It's just pushing up. The ground is not sucking you into it. Right. So normal force is only going to push up and away from the inclined plane. And so it cannot help stabilize the situation. You're going to have a net torque, and it's going to rotate. There you go.